V and A, for instance, so our velocity and our acceleration do not belong on a three-body diagram, excuse me. Right, so they have to be drawn separately. So if I were to draw some velocity vector for this, right, I would draw it somewhere that is not attached to my little point, right? I would draw it off to the side. Okay. So let's talk about work for a second. So there's a couple different situations where we have work. Excuse me. In the case where I have a constant force, work, which has units of joules, by the way, is force times displacement s, or sometimes it would be delta x, or delta y, or delta z, or whatever displacement direction that we're talking about. If this is in one dimension, and we have a constant force, and then because this is a dot product, we just get f times s times the cosine of the angle between those two vectors. So for instance, if I'm pushing my water bottle across the table, right, but I'm exerting some force that's a little bit down and into the table, right, I have to then take the dot product of that vector with the displacement vector along the table. And there's an angle between those two, phi, and that's going to give me the work done for this particular situation if I'm exerting a constant force. Right? If there's no displacement, if s is equal to 0, right, so if I push it across the table, right, doing some work, and then I push it back across the table to its original position, if I do both of those things, no work has been done, right? Because in terms of the way that I've defined displacement, this would be positive, this would usually negative displacement, right? We usually think of to the left as negative, and then some positive displacement back to 0, and so the sum total displacement, S, would be 0, right, for that situation. Okay. So if I have a varying force in one dimension, instead of a constant force, then I have to change things around a little bit. Or I have to make a little bit more general version. In this case, I have to do an integral from whatever my position is x1 to position x2, and then the force that might be varying over that distance, I have to take an integral in order to get the work done. I should just put up here. So that's units of joules. Now, there's a third situation where I can have a nonlinear path, right? So instead of a one-dimensional path, then the work would be given by an integral from position 1, P1, or point 1, to point 2, and then I have this F vector, and then I have to take the dot product with DL, and then do that integral over some path that has a line. Right? I don't think we did too many problems like this, but I'm just mentioning this in here. And so that's it. Instead of now traveling in one dimension with some varying force, now I have the potential for the force to vary, but I also have the potential for my path to vary. So maybe I'm moving my water bottle this way, and then out towards you, and then back over this way, right? And so I've moved in 2 dimensions along the table, right? So then I have to do an integral over that path. So that's the DL represents. The L is representing where am I going along that path. And you have to do an integral for each portion of that path, right? Or you have to do a portion of an integral for each of those portions of the path. I would likely not give you a 2-dimensional work problem on the final promise. Okay. So one of the things that we had that was useful for work was that we had the work energy theorem. So work energy theorem basically says that the total work done is equal to K2 minus K1, or delta K, where big K represents kinetic energy. So whatever my change in kinetic energy is, gives me the total amount of work done. So if I can figure out what the work is done, then I can determine how my kinetic energy has changed, or vice versa. Or if I determine kinetic energy, I can determine what work has been done. And so kinetic energy, sort of as in terms of just motion in 1, 2, and 3 dimensions, is just given by instantaneous kinetic energy as 1/2 mv squared. So 1/2 the mass times the speed squared. So that's not going to give us, that's not dependent on direction. This is an energy again, just like we had an energy before for work. So this is just giving us, a scalar value in joules. So this also has units of joules. All right. An additional quantity that we might be interested in sometimes is how much energy is delivered as a function of time, and that's called power, right? So average power is equal to some change in work over some change in time, delta t, and then instantaneous power is given by, you guessed it, the derivative dw dt. And that also can be found by taking the dot product of the force and the velocity. So that can give us the power. So in addition to kinetic energy and work, which can change kinetic energy, right, we can also have a change in potential energy. And there are 2 different types of potential energy that we talk about. As I misspelled things, hold on. So gravitational potential energy and elastic potential energy. So our gravitational potential energy, if we're close to the surface of the Earth, is given by mgy, or sometimes mgh, depending on how we define it, right? And one of the essential points of this is we can choose any 0 points, right? It doesn't matter where we choose our 0 point to be, because we're assuming that for near the surface of the Earth, that little g is constant, right? So all we're interested in is some change in the gravitational potential between 2 points. So say, for instance, between the top of the building and the bottom of the building, when you drop a ball off the top of the building, right, its gravitational potential changes as it drops. It has some large gravitational potential at the top and some smaller gravitational potential at the bottom. But I can choose my 0 point, say, 50 meters above wherever I dropped it, right? And then it would just go from some negative gravitational potential to some larger negative gravitational potential as I drop it down, right? There's going to be a decrease in gravitational potential as I go closer to the center of the Earth or closer to the ground, right? And there's going to be an increase in gravitational potential as I go up. But wherever I choose my 0 point doesn't matter, because for the most part, in most of these problems, I'm only interested in that change in gravitational potential. And then the elastic potential is equal to 1/2 kx squared, where my k is my spring constant. So I have this later on, but I'm going to put it here. So the k is also coming from Hooke's law, which gives us the magnitude of the force due to a spring, which is minus k times x. All right, so basically that's saying that it's a restorative force that is related to the position in terms of how far my spring is extended or compressed away from some equilibrium point. That's what my x coordinate typically means. Usually we say that x is equal to 0 at the equilibrium point. And then we can either compress it or extend it. And therefore the spring will then exert a force that will bring us back to that equilibrium point, no matter where I've put it, or where I've extended it or compressed it. Okay. So we got these two different types of potential energy. And in a system where we only have, say, for instance, gravity acting on something, or we only have some elastic force that follows Hooke's law acting on some object, then we have conservation of mechanical energy. So in other words, we only have conservative forces acting on our object. So conservation of mechanical energy. So this means that there's no friction, no air resistance, and all the forces are conservative forces. We don't have liberal forces in physics, sorry. Just conservative forces. All right. So K1 plus U1 would then be equal to K2 plus U2. So at some point, at time 1, we have some kinetic energy and some potential energy, could be gravitational, could be elastic. And then at some point later, we have some kinetic energy and some potential energy that could again be elastic or potential, or maybe a combination of the two. Okay. And as long as I have only conservative forces acting on some object, then I get conservation of energy. So for instance, I'll give you an example of having both of them together. I probably won't put this on the example, but just an example. So say I have a mass attached to a spring. Most of the time, we've had a mass attached to a spring, and it's on a nice level plane, and we've usually said there's no friction. And therefore, it's a conservative force. All forces are conservative, right? And because that makes it nice and simple, because as it oscillates back and forth horizontally, there's no change in height, and therefore there's no change in gravitational potential, right? But I could have that same situation. I could take that mass on a spring, oscillating back and forth on a frictionless surface, and then tilt that surface, so now it's a mass oscillating on a spring on an inclined plane. Still no friction, and still no air resistance. So I've just got spring force acting on that object as it oscillates back and forth, and I've got gravity acting on that object as it oscillates back and forth. So there's a combination now of elastic potential and gravitational potential, but it's still conservative. It would still obey this conservation of mechanical energy, as long as the plane is frictionless, right? Because I can't introduce any friction. All right. Now, more generally, so that's just conservation of mechanical energy in the case where we have all conservative forces. More generally, we have the law of conservation of energy, which says that whatever change in kinetic I have, if I add that to my change in potential, I might have a combination of potentials, and then I add that to some change in internal energy, U internal, altogether that is equal to 0. And U internal usually refers to heat, or energy that's quote-unquote lost due to non-conservative forces. Yeah, so you can say that that's work done by non-conservative forces. You can also say that. And as I mentioned to you in class, this is just looks like a pretty simple equation. Looks like a pretty simple equation, but it's actually a pretty fundamental and what am I trying to say? What's the word I'm looking for? It's actually pretty staggering to think about this, right? This says that whatever I do in the universe, whatever I do, I can't create or destroy energy. Right? Doesn't matter. On the scale of